Hi, everyone. We will start on top of the hour. Thank you for coming. And this will be a really interesting room regarding climate. So, and a really important one because, we need to, if we have drought, we don't have food. And I don't know if anyone realizes, but in France, actually, it's the first time they have a winter drought, a very severe one. And yeah, France is pretty north relative to other countries. So we know that drought will be a problem, and to have good predictive models are really important. So I'm really happy that Felsche, she offered to come here and talk about this topic today. So as I said, we'll start in around 8 minutes. I left the article links. It's actually 2. I don't know why they are meshed up together. Let me just post them again. In the meantime, please check them out. I will post the presentation on top of the room. So here's one, and there's the second one. And so they are separate. Good. And yeah, we'll start shortly. Thank you for coming. Feel free to share the room. I think this is a really important topic. So the more people that learn about this, I think, and how we can use AI in this field is really interesting and important. So feel free to share it. Thank you. Okay, the presentation is pinned. Thank you, Heidi, Dr. Heidi. Yeah, and feel free to raise your hand to come up to the stage to ask questions. And yeah, the more people participate in discussions, I think the more interesting it usually is. So, and thanks for being here. I hope everyone had a great weekend and is well rested. I feel like sometimes weekends are more draining than the week when the kids are home and everything is chaos. But yeah, I hope for everyone else it's different. Well, this week also my kids are home because they are off. So if you hear dogs barking and kids playing in the background, I apologize. But I live in the city. It's an apartment. So you will hear it probably. Yeah, I hope everyone can access the pinned presentation. Feel free to check it out. For me, it takes a little bit to load, but then it works in the end. So I hope that's the case for everyone. If not, please let me know. Then I have to compress the file. Thank you, Heidi. Dr. Heidi. I have autocorrect issues all, so don't worry about it. Hi, Elisabetta. Do you want me to
Hello.
say Eli or Elisabetta?
Elisabetta is fine, I think, yes.
Okay. And yeah, meet Dr. Heidi. Welcome, Dr. Heidi, to the stage also.
Nice to meet you.
Thank you, Katarina. Nice meeting you both.
Yeah, thanks for coming. We will start in around 3 minutes. So, oh yeah, you unmuted.
I
Sorry.
wonder, is Mondayitis popular in Europe as well, or it's just Australian term? You know what I mean? Is that right?
Yeah, I don't hear people using it here, at least in the US, a lot. I don't know, Eli. What do you think
Sorry, I couldn't understand it. What was the question?
about how you feel on a Monday? Like,
Ah,
I was just
yeah,
chatting.
yeah. I think it's always the same, depending on your weekend, right?
Yeah, exactly. I was saying I hope everyone feels, very rested from the weekend, but most of the time I feel the opposite way because the kids are all home and it's chaos. But yeah. But yeah, we will start soon. I posted the papers you shared in the chat, and I added the presentation on top of the room. So everyone should be able to access it. If you want to refer to, those different files, that's where they are. And yeah, we will start in a couple of minutes. So how's the weather in California right now?
Yeah, it's rainy. It's really rainy. I'm just visiting here. So for me, for winter weather, that's okay. But hearing from others that it usually doesn't rain, yeah, makes me also wonder when it's gonna stop. So today I opened the 10-day weather forecast, and it said just rain every day. Yeah, so very unusual for those regions.
Yeah, I think it even snowed, right? In some places.
Yeah, there is snow in the mountains, so you can see it from if you have a little bit of view on. I don't know. It's also not that high mountains here, right? But there is still snow, so really unusual winter. But let's hope for a nice blossom, so like that. So I read yesterday that there are high hopes for super bloom this year, so maybe that's going to be kind of the good part about it.
Oh, that sounds great. That sounds beautiful. Unless you have allergies, then
That's true.
wearing a mask probably helps.
Yes,
You
yes.
can see the pretty flowers, but you don't have to sneeze.
Yeah.
Maybe your eyes, but that's it.
How's the weather at the East Coast?
Well, it's unusually mild this year. I mean, it snowed like so little. Most of the time, it's above 0 Celsius. Yesterday was 10, I think. The weekend before was like 14 and sunny.
Okay.
And then in between, it's kind of like 4, something like that. There were very few days where it was below 0. Yeah, it's unusual. Last year was already pretty mild, but I believe this year is even milder. So I don't know. Well, I guess we knew that this would happen, right?
Yes, yes, that's true.
It's
Weather
like
out of equilibrium. Something's off.
yeah, exactly. I mean that it doesn't snow here, but then I believe in LA that there was snow. That's really,
Yes.
really weird. I kind of liked New York. Probably most people don't. I liked that it had a really hot summer, but then also a really cold winter with snow. I like that, that variety of weather. Because where I grew up in both places, in Germany and in Portugal, it was just rain in the winter. Like, it was just depressing.
Yes, actually, winter with real snow is way better. That's also what I think, because gray and rain is not pleasant, but with snow you can do so much outdoor stuff. You can actually enjoy the weather
Yeah.
and not be like, okay, just stay home.
Yeah, exactly. Rain is really annoying. I think we can start now. So
Okay,
good
perfect.
that we chatted about the weather because it's kind of a climate room. And I know people will keep coming in, but let's start with introductions and then we'll go from there. So, welcome everyone to Science Society, and of course, a special welcome to you, Elisabetta Felsche. And before we start, let me give the audience, a little bit of information so that they know you a little bit better. And Elisabetta did her double degree, bachelor's degree in physics and philosophy in Munich, and with a very excellent grades, especially in Bavaria. If you have an A, that's like I think it's you cannot achieve a better grade in Germany. And then she did a climate research intern in Montreal in Canada at Oranos. And she also did work in IT at the Allianz in Munich, Germany. And she then also started as a PhD student at the Department of Geography in Munich. And she finished her master's in physics in Munich, Germany, in working in climate sciences and machine learning at the same time, which is, I think, really interesting that you combine these two expertise for this field. I think that's really interesting. And Elisabetta also received scholarships from the Bayerische Elite-Akademie, and she was a holder of the Deutschland Stipendium, and she was also the co-founder of Me.Now, a project for stress reduction in schools, where she had the role of main project manager, which is also really interesting. I will ask you about where you worked in, designing workshops for different schools in Germany. And you are also the counselor at the School of Investigators Dialogue. So you have a really interesting and really diverse curriculum, which I love. So, the first question would be, how did you discover these different passions in your life? Like, did you start with one and then one thing led to the other? Were you always that you had different interests and just had the energy to keep, different passions going, and then kind of figured out to combine them together? I think it's really interesting to learn from you. Thank you.
So first of all, very happy to be here. Thank you, Katharina, for the invitation and the kind introduction. And also happy to be sharing a bit more about my research here and non-research. So thank you for all of you being here. And concerning your question, Katharina, yes, I have a very multidisciplinary background. I think what kind of always drove me is that I want to kind of do good. I want to contribute to kind of the pressing issues they are. So kind of currently, besides my PhD, I'm also working in entrepreneurship education. So I'm really working with people that want to kind of change the world and make it a better place. And I think this is what kind of also followed me through my CV. So kind of I worked a lot with young people, so with school children in this Me Now project, or with adolescents, which was the case as a kind of summer school counselor. And so what I found always striking there is that I knew I kind of can make an impact there by showing them access to new tools, helping them kind of discovering themselves, or like in the stress reduction project, on showing school children strategies on how to cope with stress, because this is actually a topic which will follow, like, I think everybody of us through their whole life. And also then coming to science, for me, it was crucial to pick a topic which is which is pressing, because I started off my research in particle physics, and I truly believe that also in particle physics there are huge discoveries to be made, but I kind of compared for myself, where can I make the kind of the biggest contribution, and this is basically what led me to climate science, and what left me kind of also there, and that's why I also pursued it in my PhD.
Yeah, that is wonderful to hear that you followed your passion and you were very purpose driven. And I think that's the only way one can find the energy to do all these things, because every single one of them needs a lot of energy and expertise. So I think the only way to achieve that and to keep it going, right? Not just to achieve it short term, is really purpose. So, yeah, congratulations. And yeah, it's wonderful to hear that you also received the opportunities to do that. What do you think was the most important opportunity, or which were kind of the key points that allowed you to to pursue these different things? Because you can have sometimes like really bad luck, and you have a supervisor that kind of doesn't agree you doing anything else, or funding. So what do you think were kind of the key points for you?
So, well, it's hard to tell. I mean, I think it always starts a bit with where you come from, and I was incredibly lucky to come from a family where I had very strong female role models. So as well, my grandmother as well as my mother were both working actively in science, and so for me it was never a question of whether a girl can do something like that. So this was completely clear, an outlet there. So I think, just to say that there, I'm super lucky. And then I think going to Uranos to Montreal was a really good experience for me, because I had a great supervisor who was supporting and actually seeing me in the field. So I was coming from a totally different background, right? I was coming from physics and then coming to climate. It's, I mean, of course it's connected, it's the same physical laws, but it was a generally new domain for me. Yes, and so last but not least, then coming into this innovation field, where I all of a sudden saw, right, no matter which field you're in, you can do innovation there. You can think of new ways, and you can combine new ways. And this is an incredibly fast-lived and really great environment where just everybody is interested in what you're doing, and supports you on your way. Yeah, so maybe this is what I would call kind of the corner experience, like key experiences that you asked for.
Yeah, that's wonderful to hear, and to see how important role models are, and then also support, which I think the emphasis, at least here in the US, is way too often on if the family had money or so. But I think if you have the right role models, yeah, if you can imagine yourself doing something, that helps a lot. I think even a lot more, because you can have a lot of money but still don't think you can succeed in
Yes.
something. So so yeah, thank you for sharing that. That was a really interesting interview, and a very, I think, different than others. So thank you for sharing that. And yeah, the presentation is pinned on top of the room, so everyone please access it. And Elisabetta, the stage is yours. Thank you.
Perfect. Let's get going. Thank you. Yes, so just maybe before you open the presentation, kind of the first introductory part will not be on the presentation, so welcome to listen like that, but I will say when I will be coming to the presentation. So what I want to talk today about is kind of my 2 research projects that I have been conducting and publishing so far. And the overall topic is to use AI to understand heat wave and drought formation, because I really believe that there are many ways in which kind of machine learning method can help us, especially if you imagine, right, we live in a very data-rich world, and we will have way more data the longer it goes. So we kind of need to find the tools that will actually help us to understand the physical systems. And so I focused on heat waves and droughts. So let's start off maybe with a question: why is it important to look at heat waves and droughts? Well, my research is focused on Europe, so we have had there kind of for the past 20 years, for sure, every 2 or 3 years, we have a major heat wave happening, and a lot of times also accompanied by a drought. So 2003, 2010, 2018, just to name a few. Also in North America, we have had this problem in the past years. So 2000, kind of actually the last summer, so 2022 was exceptionally hot. Multiple temperature records were surpassed in the United States. This lasted actually for one whole season between May and September. So a very huge and long event. Also not too long ago, 2019, there was a combined heat wave and drought in September, October, kind of around Colorado and central United States. That actually, it was not just a heat wave, but actually also an exceptional drought. So just also to name in the beginning what I will be talking about. So what do I understand behind those events? So a drought is generally a deficit in water, and we can define it in multiple terms. It can be a meteorological drought, which means there is just too little precipitation. It can be an agricultural drought, which means there is not enough soil moisture for crops to grow, or it can be a hydrological drought, which means that are kind of our water reservoirs and our water catchments don't have enough water. Then on the other side, heat wave, also an easy definition here. I think that it's just a period of abnormally high temperatures. So usually one would take their 90th or 95th percentile of mean temperature or of daily maximum temperatures. And we say that in climate science, like usually heat waves should be at least 2-3 consecutive days, but we know they can last for weeks or months. And usually a heat wave takes place when kind of there is a high pressure system that develops across one region and that it persists over that area for a long period of time. And so maybe also to take a step back here and also to look a bit into atmospheric science, what does it mean? So I would like to talk a bit about the jet stream, right? So probably most of you heard that kind of the jet stream is this strong wind blowing from west to east. And in the northern hemisphere, it's basically transporting the weather. So it's transporting the high and low pressure system from west to east. And usually the way it goes, that it's just alternating, right? That after a high pressure systems comes a low pressure systems. So basically after kind of 5 days, 10 days of sunny weather, we will have a period of rain, such that our whole climate and vegetation systems can come again in equilibrium, have enough water, again saturate, and then again it will need the sunlight. And so the jet stream is flowing in the troposphere, so it's around 10 kilometers above the surface of the Earth. And what I actually really like is this comparison of the jet stream to the highway, right? It's just the atmospheric highway, which brings us the weather. And so it can also happen that there is a traffic jam at the highway. So basically that our cyclones and anticyclones traveling on it, staying there for longer. And just to mention here, an anticyclone is the same as a high pressure system, and a cyclone, it's the same as a low pressure system, just not to confuse anybody here. So basically when a heat wave, so just to connect to the heat waves here, when a heat wave develops, that actually means that our jet stream somehow changed its way, or maybe that the incoming low pressure system was not strong enough to move away the high pressure system such that it persists. And it happens on a regular basis, such kind of an event. So this is basically when a heat wave develops. So such kind of a weather pattern is called an omega weather pattern or blocking, and it prevents kind of the rainy weather from coming in. And if you're kind of interested in basically looking how our weather daily looks like, there is a really great resource which is called earth.nullscope.net, where you can have a look at jet stream and all different climate variables. But I'm happy to post it in the chat maybe a bit later. But first, to kind of follow along, so now I explained, right, that we have this jet stream and that needs to have a blocking event for a heat wave to happen. However, does it mean we can actually predict what's going to happen? Unfortunately not. So I think all of you know that the weather forecasts are limited to around 10 days, but basically we also know that like beyond 5 to 6 days, we don't need to be too concerned about it. And the reason for that is that although we know what kind of processes dominate, still the system is so complex and has so many little interactions that we don't know which effect is going to be leading to those major events. So on the regional scale, we have a lot of interactions which can play a significant role, but also on the global scale. So for example, we all know that after volcano eruptions, there's usually a cooling because kind of the particles from volcanoes prevent the sun, the solar radiation from coming in. So there's a cooling effect. We know that our ice sheets are melting. That means that less solar radiation is reflected back, right? White surfaces are good in reflecting solar radiation, which means that basically more warmth is reaching the Earth. And then we have kind of always the clouds interaction. We have the precipitation. We have our water catchments and also atmospheric currents, which are influencing the weather. This is such a huge and complex system that basically on the large scale, we don't know what's going to happen after 10 days, and we for sure don't know what's going to happen next month. And kind of one more note on our atmospheric system is kind of the interaction between heat waves and droughts. So we know that kind of a drought can trigger a heat wave and the other way around. And the way it works is that basically, so let's imagine we have first a heat wave. Then this, of course, leads to higher temperatures on the ground, which leads to more evaporation, which leads to drying of soil. So basically, because of the heat wave, a drought can develop. But it can also happen the other way around, that we have first a drought, which leads to kind of in general less moisture in the atmosphere, which leads to less clouds, and which again means with less clouds, more solar radiation will be coming in. So again, a heat wave can develop. So this all said, kind of one last remark before I also can jump to the slides is basically that the events we want to be looking at and the events of heat waves and droughts are very rare. And if we kind of have a look at observational data, actually our records are very limited. So let's say we have temperature records, I think, for 150 years, for the past 150 years. And we're looking at events that happens maybe once per decade, right? Which will lead us to maybe 15 events to study, which is a really, really small number if you want to do statistical analysis with. And given the high uncertainties of the system, it's even more complicated. So kind of the overall approach of the study and the work is actually to also look at model data where we can generate artificially way more events, and from that to understand the physics better. But you will understand in a moment what I mean with it. So now you're welcome to jump into presentation. I'm on slide 7, motivation and research questions. Let me look at the chat. Okay, there is, I think, no other questions. Yeah, so if you have any questions also, you're welcome at any time to type them in the chat and I will have a look at them from time to time. So what do we want to understand? So the leading research question here is, what are the factors that contribute to the formation of heat waves and droughts on the regional level? And basically to understand what we can learn about those events from big data sets with the help of AI. Of those great events. So coming to the data we're dealing the special project is that we actually have access to a 50-member single model initial conditional large ensemble, which means that we have our data available not just one time, but 50 times, right? So as I mentioned, if we would have just one kind of, as with observational data, it is the case, we have just one realization, we have too little statistics. And that's why we make those model runs not just one time, but 50 times, which lead us just to kind of gives us the possibility to study the extremes. And that also gives us the possibility to understand how the mean develops in terms of kind of climate change. So this is a model which is kind of reproducing our world. So we have all the continents there, we have all the oceans there, we have all the interactions in the system. And the way those 50 members are generated is by having small perturbations. So basically changing a little bit our initial values we give into the model, we get very different outcomes. And we have a look at a time frame of around 30 years of historical climate. So it's 1981 to 2010. And we use their variables like daily maximum temperature, soil moisture, and precipitation. And we also do, of course, validate our results because we know that the model should be related to real world. We also do validate them with observational data sets. So now I'm on slide with number 9. So there are two research projects. First one I will be talking about, it's about predicting droughts for two domains of Munich and Lisbon. And the other is on typical heat wave patterns and how they're connected to soil moisture. So I would start off in the first project after a small, give me 5 seconds. So what we basically did in the first project is kind of naively asking, can we predict droughts for these domains? And basically taking all the variables we were given. So we were taking 27 monthly atmospheric and soil variables from our model. So this is the CRCM5 large ensemble, as well as taking 5 large-scale teleconnection indices. What do I mean by that? So there are variables that are not kind of given locally, but they're describing in what state the overall atmospheric pressure system is. So basically all those kind of short initials I'm giving there. So North Atlantic oscillation is now, SCA is the Scandinavian oscillation, and so on. They are kind of giving us the overall state of the system. And they can be actually also really useful for the prediction because they're not just locally, but they're also saying us how the overall atmosphere is doing. So on the right, I have also attached a picture on how those modes look like. And we're trying to predict drought with a lead time of 1 month using artificial neural networks for the prediction. And after a lot of training, we were able to obtain accuracies of 57 and 55%, which are moderate, but truly believe it can be done better in future models. However, we understand this is not a forecast which is meant to be for the end user, right? So if somebody would tell you next month there's a drought happening, but with a 57% chance I'm right, this is not useful for the end user. However, what we can learn from those predictions is which variables are important, right? And then using those variables, do again a training and evaluation, and then maybe arrive sometime at at higher precisions and higher accuracy. So going to the next steps, what we did is applying the Shapley method, which is, if you're not from the machine learning field, it's basically a way to look at which variable is important for the prediction. So where does the model take its skill from? So what we're getting is that for Lisbon, we have the sea level pressure, surface pressure, and North Atlantic Oscillation 1, which is this teleconnection indices, important for the prediction. And all those variables are important just 1 month before the drought is happening. Everything else, everything before, is not that important. For Munich, we have a similar result, but also another variable is important, which is East Atlantic Western Russia oscillation, but 5 months before the event is happening. And this is actually really exciting because here we have not just variables important 1 month before drought is happening, but also 5 months, which gives us a way longer period. And so kind of as a last step is in the study, what we did is to have a look at those variables in terms of seasonality. So that we have a look at, okay, if the drought is happening in summer, what variables are important then? And kind of that's how we divided the variables. So now I'm at slide number 12. And so also what we see there, that this East Atlantic Western Russia oscillation 5 is actually also important in Lisbon, and that's the most important predictor for both domains and not just for Munich. In terms of others, the variables stay more or less the same. They just interchange. So sometimes it's the North Atlantic Oscillation 1, which is first. Sometimes it's sea level pressure, which is first. But everything else is more or less as we would expect. And what we also can drive from that is that kind of also soil variables are not that important, that it's mostly atmospheric variables which are telling us if a drought is going to happen. So much for my first project. Now I would like to start off into the second one, which kind of starts with heat waves and then arrives at kind of soil moisture. So to deep dive into that, let's start off with definitions. So here, first step was to understand what kind of typical modes of heat waves are there in the European domain. Why is that important? Well, because oftentimes studies use kind of artificially chosen regions. So they say, well, let's take this country and let's just make the study based on this country. However, we have kind of different atmospheric modes of heat waves, right? So there are regions which are closer interconnected, where the heat waves is rather happening at the same time, and there are other regions which are rather not interconnected. And so we wanted to find out those natural modes. And yeah, it was super useful to have this very same data set where we had the 50 members. So this led us to actually 50,000 heat waves, which we 50,000 heat waves which we could analyze. And we did it by applying hierarchical agglomerative clustering. So again, a machine learning method, which kind of is clustering similar events together. And what we came up with were those 9 different heat wave patterns, which you see on the right of slide number 14. So I want to just name it one time, because I'm not sure if everybody has the presentation in front of them. So it's Iberian Peninsula, which is above Portugal and Spain. There is Western Europe 2, which is kind of combining southern France and northern Spain. Western Europe 1 above France and Germany. Then the British-Irish cluster. Then the Southeastern Europe cluster, which is the region above Balkans and Italy. Greece, South Italy, Scandinavia, Central Eastern Europe, and Northeastern Europe. So those are the 9 distinct clusters we found. Then we were wondering, okay, we find them in the model data. Do we also find them in observational data? And we did this in kind of different ways. One time we also performed clustering in observational data and were able to compare the clusters. However, what I want to show here is more the comparison with historical events. So on slide number 15, this is from a publication by Rousseau on the 10 most extreme European heat waves. And there we did a matching of those historical events, historical heat waves, with our generalized clusters. And we actually argue that we are able to find a very good correspondence there. It's of course not true for all of them, because some of the heat waves are outside of our domain. There's also one event in July 2006, which is kind of spatially super distributed, but actually all others we're able to find a really, really well matching. And this was also actually interesting for me, because what the clusters are, they are kind of a mean of the system. However, we see that also in terms of historical heat waves, they are just a manifestation of the same pattern. So this was kind of a validation step. So kind of the question we were trying to answer there is if those patterns we're finding are meaningful, and we can say yes, they are meaningful and we can find them in the real world. And the last step was to have a look at those clusters we're finding and see what we can learn from them on kind of this, again, topic of predictability. So what we did there is to focus on the soil moisture. And so we went kind of for every single cluster, we asked ourselves, how is the occurrence of a heat wave in this specific region, in this specific cluster, is connected to a soil moisture deficit in the season before the heat waves happening, in the season during the heat waves happening, and after the heat wave. So we did this by actually for every model year, we're looking at counting how many heat wave days were there in this specific cluster, and kind of connecting it to a soil moisture anomaly in the season before the heat wave, during and after. So if you're wondering so I'm on slide 17, if you're wondering what the abbreviation is, so JFMA is January, February, March, April. So these are basically the months, the seasons we're looking at. And we did this by applying the method of quantile regression, because this allows us actually to have a look at the more extremes. So basically what it does is that it's not just kind of making a regression of the mean, but it's also looking at if for more extreme quantiles, so for example, for kind of higher number of heat wave days, if there we can find a kind of a regression line, a kind of, I don't know, negative or positive regression line, which tells us that in the mean there might be no relationship. However, for those more extreme events which we're looking at, there we can find a relationship. So going to the results of this very last part on slide 18. Here on the left you see the quantile regression slopes for those three regions. And kind of slope means the more negative it is, the stronger the interaction here between high number of heat wave days and less soil moisture. So what we can find there, and actually here just the significant clusters are shown, that soil moisture deficit in spring in the regions of Iberian Peninsula, Western Europe too, Southeastern Europe and Greece, which are basically all regions in the south, that there kind of after a very dry spring, there's a higher chance to have a very hot summer. And basically the way we're interpreting it is that actually in those regions we have a limited soil moisture, and that those link I have been describing before, where a drought is triggering a heat wave, is true for those regions. And this is basically the interaction we're dealing here with. And this is actually also really interesting that kind of by having a look at the soil moisture, we might be able to predict heat waves in summer for those southern regions. So this was the first season we were looking at. Next season is kind of basically soil moisture during the heat wave, slide number 19. This is actually more proof of a concept. So we see an effect for all the clusters we're looking at, and basically the longer the heat wave, the stronger the soil moisture anomaly, and other way around. So not that exciting, more proof of concept. But last but not least, also really interesting to look in the next season. So what we do there is it more probable to have a soil moisture anomaly, a negative soil moisture anomaly after there has been a heat wave in a region in summer. And yes, we do find it for just some regions. So we do find it just for northern clusters, so Scandinavia, Northeastern Europe, as well as for Eastern cluster, Southeastern Europe. And how we're interpreting it is basically that in those regions, it kind of takes, after a very hot summer, it takes until the next season for the soil moisture to fully recover. So it's more probable that we will have a drought after a long heat wave. Yes. And yeah, I think that's it on the results of the second study. So you can find an overview over the study on slide 21. And I would just like to summarize with kind of what we have learned from our studies is basically that on the one hand, in terms of drought, we can say that predictability of droughts, it's really varies across seasons. So we actually, and regions, so we have to go into the specific regions and seasons and then investigate on which variables are important for the predictions. We learned that in summers, we have even a predictor, which is East Atlantic Western Russia oscillation, which is 5 months before the event is happening, which allows us seasonal prediction. And it's interesting to look at why this index is actually so powerful and meaningful. Then we have learned that soil moisture droughts in Southern Europe in spring can serve as a predictor for long heat waves in summer. And on the other hand, that in Scandinavia, Northeastern Europe, or Central Eastern Europe, after prolonged heat waves, there is a higher chance of also of a soil moisture deficit in the following autumn. And kind of zooming out, what I hope to show with this research is that machine learning models, AI models, help us to gain insight into factors leading to extreme events, and that this is crucially important to make better seasonal predictions of extreme events. Thank you so much. And sorry, I have not been looking in the chat, but maybe let's do it now.
Oh, yeah, thank you so much for presenting this really interesting and amazing work that you did here. Really appreciate it. You explained it really well, how you used the different data sets and to create this predictive models. That's really interesting. And I was really surprised by the amount of actual severe weather events data sets there were available. That's really interesting. So just to make clear, like for the audience, how long time-wise do those go back, those data sets, and does the frequency of data sets increase in the last years, and could that maybe be problematic, that there is maybe more data sets from recent years, the higher frequency, would that somehow make the model different than if there would be a lot the same amount of data sets over the whole time scale you're using, and what the time scale is?
Maybe just to distinguish here, so we have, of course, we have kind of the data sets. So on the one hand side, we have the data sets based on reality, observational data sets. This is always, so they're not getting bigger, right? They're just getting more precise because we're able to measure in a better way the variables. However, the problem with observational data sets is that on the one hand side, they don't provide that much data as mentioned, and on the other hand side that we cannot have all the atmosphere, all the variables we're looking at, we would like to have, because for example, just take air pressure or atmospheric winds or actually soil moisture. It's really hard to measure soil moisture on a big scale. So that's why we're using models, because models are able to give us all the variables at the precision we want to have them. So basically the model we're looking at has a very high precision of 12 kilometers. And this is great because especially maybe if it's kind of very habitated regions there, we would have such kind of a precision, but for northern regions, for example, or for deserts, we just don't have that many measuring stations. So yes, if you look at model data, more and more model data is being generated. However, kind of you always try to focus on the most recent data. So that's why it's not kind of exponentially rising, but you rather would look at, okay, what is the data set that is best representing the atmospheric circulation, that is best representing the land atmosphere interactions. And yes, the trend is kind of also to go into this large ensemble creations, which means that you basically generate terabytes of data, where machine learning is actually useful to analyze that. I hope I answered your questions.
Yeah, thank you. And so do you think, well, are we starting to use sensors maybe in soil in different spots, or is there, did we do that already? I'm sorry, I don't know, that to get more accurate soil moisture data, or do the current weather sensors already, are they already able to spot it relatively precisely?
I'm not sure if I understood the question. So I think, yes, there's of course a lot of development going on, but I think it's just too much of an effort. If you imagine to have a 12-kilometer resolution, I mean, you can do it for one country, but how do you make sure that actually big regions are covered? So I think that's kind of one of the key issues. I think where there's a lot of potential is actually by using space images, by using remote sensing to estimate those variables, because then you have also kind of the whole picture, right? But then there are again problems. What happens if you have, I don't know, clouds in the way? So I think different methods are needed. So it's probably the way forward is probably not to have those not to have way more of those measurements on Earth, but rather doing it from space, because then you can also ensure consistency.
Yeah, I'm asking because at the Oceanographic Institute in Woods Hole, I was at the marine biological one, and we had like shared meetings. This is years ago when I was a postdoc there. They started to measure the green, like the color of the green of leaves and different plants, to make also predictive models and how well plants are doing, crops are doing, forests are doing. And I was wondering if those shades of green, maybe, for example, could be used, or other, more, because we are developing fairly cheap sensor technology for personal health use, and then also for all kinds of stuff. So for agriculture, this type of modeling, to have this precise and to extended future, will be really important, probably, for survival of a lot of people. So I was wondering if there, if that there's a lot of development or effort to put in good sensors in different places where it's important.
Yeah, so as you basically described it, that kind of as in the oceanography research, it's important to have a good kind of Earth representation, to know where we are dealing with which land cover. Important to calculate the kind of the solar radiation reflection, as well as, of course, what kind of land cover it is, how it interacts with atmosphere. So yeah, for sure, there's a lot of research going into this direction, into kind of precision of the measurements we're dealing with.
Thank you so much. And yeah, a lot of people joined the stage for questions. So yeah, please go in PTR order, everyone. So I think Joyce was your first, then Deepak, Aya, Armish, and Eric. Welcome to the stage. And yeah, go ahead with your questions. Thank you.
Okay, yeah. First, thank you for going into this field. It's so important to have really smart people going into this area because we all know this is a really crucial problem with climate change. I was going to say I actually have a background years ago where I was at Oak Ridge National Laboratory and I had a postdoc and it was related to the climate. And 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 I remember learning a lot about systems thinking and systems theory and modeling. And one of the things I thought I would mention, just for people who aren't as familiar, um, the issue with the short-term forecasts for weather, at least one of the big problems is what is sometimes called the butterfly effect, where the initial conditions have a really huge effect when you follow over time. And so you'd have to know so many different variables so precisely to predict a really long time in the future. And so anyway, it's really great to see that different approaches are used that, say a variable like soil moisture is a more of an integrative variable that integrates a lot of information into it. And so it makes a lot of sense. And so I'm really glad that you're using these new techniques and AI and machine learning. And anyway, did you want to make any comments about the sort of butterfly effect and the problem with temporal modeling of that kind? Anyway, thanks. I'm done.
Thank you very much, Joyce. Can you please repeat the last two sentences because my internet connection, I think I didn't hear you well.
Okay, well, the last part was just, did you want to make any comments about that sort of issue with modeling and the sensitivity to initial conditions and how you've dealt with that? Anyway, just
Yeah,
that's just the general idea.
perfect. Thank you very much. Yes, so the way I was dealing from it, so I'm not kind of a modeler myself, but the way I'm dealing with this is by actually exploring this ensemble spread, because actually what you, Joyce, introduced so nicely, this butterfly effect, is that what you of the project where this data is created from is actually to estimate how actually climate change also in future is going to change the mean of our climate system, but also the extremes. And what we see there is that this whole model starts from like different butterfly effect kind of differences in the initial conditions, and then we see yes differences in the mean temperature of 1 degree or so. And this is a lot, right? So because currently our climate change from pre-industrial times is around 1.3 degrees. So what this butterfly effect in the end means is we see a great effect of the we see great effects of climate change, or we see none. And this is actually in parts how much it varies. However, what we also know is that kind of also with the most cold models of our 50 members, by the end of the century, we still have a climate change effect. We just kind of now can estimate the range in which it will be. Yes, so that's kind of the one perspective, like from the modeling side. Unfortunately, I can't give you more insights.
Thank you.
I think I'm next here in
Yep.
DTR. Yeah, hi. So as a follow-on, I guess, to that question, I've been looking at NCAR, which is a research facility in the U.S., I'm sure you know, that looked at drought. This is actually quite a long time ago, and they did predictions for 2030s, 2060s, 2090s. And in the 2060s, they had a Palmer drought index of like -9 across a lot of the US and a lot of Southern Europe and other places, which is like 3 times the 1930s Dust Bowl. So to me, this is some of the scariest climate predictions that are out there, and it's not one that's talked about really much at all. So I'm just wondering, have you looked at long-term forecasts for drought, and does that kind of number that I just quoted seem about right from what you understand?
So looking at Europe, so what I can share there for sure is that with kind of the current emission scenarios, if kind of everything goes as we're expecting it to go. So what I mean by that is that basically we continue emitting CO2 on the rate we're emitting now, that basically the drought severity will increase by around 2-3 times. So we don't have that kind of an event which we can compare to, because I think the Dust Bowl was actually a very huge event for the US. But that would actually mean that there is a kind of a shift in climate zones and climate regions, that basically the way it is now in southern Italy, that's how northern Italy will become. So kind of everything is shifted more up, and then we'll basically need our whole vegetation system will need to adapt, and this is very scary. However, I think like from recent research, we still have the chance of kind of making the changes that by introducing mitigation measures now, we won't see the effect immediately, but by the end of the century, we will actually be able to get back to more or less normal situation. But yeah, that's how it is with extreme events. We can't say if the event is happening because of climate change, right? Also, Dust Bowl happened almost without climate change.
Right. Well, right, but it was. I'm not sure about what you just said, though, because even with mitigation efforts, which I assume you mean if we reduce our emissions, but climate change doesn't improve. Temperature doesn't improve if you reduce your emissions. It only stops getting worse. So what do you mean by if we have mitigation, we can get back to normal? I don't know how that's possible.
Yeah. So I mean, we can't take the CO2 out of the atmosphere again, but so we see a rise in extreme events. So because then the rise in extreme events also happened because kind of our system, so the way I understand it at least, is out of the equilibrium, and then by kind of stopping the emissions, we kind of get back a bit to a more normal system. We won't ever be back at where we've been 100 years before, but at least kind of we can have the climate is more in balance. We have more of what we're expecting. Maybe that clarifies it.
All right, thanks.
Sure, you're welcome.
Yeah, Deepak, did you want to ask a question? Thank you.
Yeah, thanks. How reliable and accurate is this AI model, and what are its limitations in the long run?
Sorry, what was the second part of the question?
What are its limitations in the long run?
So how reliable is the model? So the way one evaluates the models is rather in the projected change and not kind of in absolute numbers. So I think there we see that the model has for sure biases in terms of kind of it projects, it's a bit warmer and it's a bit wetter actually. So if this model tells there is more drought and it's actually wetter than the reality, then we kind of, it's actually also interesting. The general limitations are, well, it's hard to talk about them in general sense. That's what I would say, because actually you have to evaluate it for every variable. However, I think the good thing about the model is that we have a lot of members and that we actually can estimate that the mean is actually very reliable. So if you look at the mean, this is one of the biggest ensembles we're looking at. So usually, like a lot of ensembles are maybe 10 members or 20. Here we have 50. So I think in terms of the mean, it's super reliable. But of course, it has biases as all the other models. It's not exceptionally more biased than the other state-of-the-art models. So that's what what the results from a recent study are. I hope it answers. Thank you, Deepak.
Yeah, thanks. Yeah, thanks.
So who's next? Yeah, Aya.
Hi there. Thank you for the talk. I really enjoyed it. I'm from the Horn of Africa, Ethiopia, Somalia, and we have incidences of drought every year. So I'm not sure how useful a predictive model would be for them. I can understand it in Europe, where it's excellent for the extreme cases, and then you can, like in the Mediterranean region. But in places like Somalia, Ethiopia, where we have really awful incidences of drought, my question would be, would your predictive model be able to tell us maybe what parameter was involved in causing the drought? Could you use it in cases like that? Because we know, for instance, there is going to be a drought every year. We know that, unfortunately. But how would you use your models to help countries like that, which we know there's going to be a drought? Thank you.
Thank you very much for your question, and thank you for tuning in from so far away. So I think, so in general, if you know that the drought is going to happen, that's probably not the question of predictability, right? And this is not the big question. I think on the one hand side, there is probably still some variation, right? So it might help with kind of like local mitigation measures if you have some kind of knowledge when it's going to happen. And of course, on the other hand side, we can look into the variables leading to the drought. So yes, we can apply the very same methodology and then see, yes, kind of what variables were most important here, and then maybe understand kind of the mechanism of formation of droughts there. So that would, of course, be possible. But yeah, you're totally right that if there is no question, if a drought is happening, then there is no kind of no magic behind knowing it by an algorithm, right?
Thank you so much.
Sure.
Ramesh, go ahead.
Yep, thank you, Elizabeth. So I read the paper. Thanks a lot for your presentation. So I have three groups of questions. One is on the data collection, second on the modeling approach, and the third is on the performance of the model. So I'll just ask. I'll start with the data collection. So I can see there's 20 years of data which has been collected. I can understand precipitation and temperature data. I'm curious on how you get the calibrated soil moisture data from 20 years, because soil keeps on changing because of the deforestation and everything from the same area, from the same spot. How are you getting the, how did you manage to get the soil data with that precipitation? That's one thing. And second thing is on the modeling data. Did you have enough event rate of drought data in last 20 years so as to build a significant model? Like, did you have enough instances of drought in that sample so as to differentiate it from the non-drought events? So I believe it's a supervised model. So if you can help me understand this point. I have a follow-up as well. I'm sorry if I'm taking too much time.
Yeah. All good. Let's start into it. So the thing is that I'm using model data, right? This actually gives me all the variables I'm needing. So it has kind of on 12 kilometer resolution and on daily to hourly scales, all kinds of variables, precipitation, soil moisture, temperature, daily maximum temperature, radiation, and so on. So here, I'm sorry if that was not clear, I'm not using observation data, but model data. So that basically solves the problem of having the data. It, of course, introduces the problem how accurate it is, but there has been studies performed that actually tell, okay, what we're getting there is in the range of the observed data. And in terms of examples, so as we're dealing with 1,500 model years, so we have I think around, sorry, the study was a bit ago, but I think around 5 to 10,000 of kind of examples of droughts. So yes, it gave us kind of enough range to do the machine learning based on that. And you're welcome to ask the follow-up question, because I think you said you have 3 of those.
Sure. So Elizabeth, generally what we have seen is that the performance of these models are pretty low, especially when it comes to long-term forecasts. I mean, in short term you can forecast a bit, but in long-term forecast, the performance and accuracy of the model is such that it just, you're doing something. There are 2 plus 2, you're just adding an equation which gives you some directional. Uh, how was the performance of this
Hmm.
model, and why do you use neural network with this in such a limited data set? I mean,
Yeah, I think
yeah.
we have to distinguish here between prediction models. So I think what you meant is the performance of prediction models is low, right? The ones that are telling you how the weather is going to be in 10 days. But here, this is a totally different approach. We're trying to estimate kind of the general state of our climate system, and we're trying to understand how our climate is going to develop given climate change and given all the influencing factors. And here, we're rather trying to have an insight into kind of different mechanisms of formation of those extreme events. And then we can compare it to kind of the reality. But basically, what we're doing here is multiplying the reality, right? So, kind of having an insight into all the different weathers that might have happened if the initial conditions were different. So, this is the core idea. And so that's how we and kind of basically we use machine learning here because we just have the possibility to have so many extreme events and actually to study the interactions there given the amount of data. I hope that
Thank
clarifies
you.
it.
Yep. Thank you. Any plans of using, let's say, satellite imagery, the cloud imagery data, which might give a different angle to the problem, which might add up to this?
Well, for sure. So kind of in terms of validation using observation data, using satellite imagery, this is great. So I think the approach here would be to start off with model data and then to look to observation data if we can find similar effects that are maybe not that strong because we don't have the statistical background there, but that would give us an indication if what we're seeing there is true.
Thank you so much. I think the hope in the future is that the question which I asked, if we can take data from altogether different geography
Yeah,
and put together and
yeah.
come up with that underlying one factor which can govern these, that would be phenomenal. Thank you.
Thank you. Thank you, Amish. I think Eric is next.
Yeah, hi. Yeah, this is a fascinating area. Thanks for working on it. I work in agricultural tech, and I've paid a lot of attention over the years. There's a company called Climate Corp, which was sort of one of the original companies many years ago. Now, I guess 10 years ago. That I think what they did is something like they worked with farmers and forecast the weather for them
Mm-hmm.
and guaranteed it. They had offered an insurance policy and told them what crops to buy and everything. And I think they got purchased by Monsanto, but it's an interesting sort of business. And there's other companies out there. There's both in ag and just everything. So, do you have any? I mean, I don't know if I really have an exact question, but just sort of any thoughts on some of these commercial applications of this, especially in important areas like agriculture, where I think it's getting really difficult to grow crops because you might have like a cold snap, or like right now here in California, it's raining a bunch. Maybe that'll affect it got warm earlier. Maybe things started to flower early, and then the rains come and knock all the flower blossoms off and affect the pollination, and you get lower crop yields. And I mean, but these things are very
Yeah.
difficult to forecast.
Yeah, so maybe to share some thoughts on it. So I have been doing some work also on crop predictability, and also kind of given the current state of the climate, we really struggle to predict it, and then even going into changing climate, it might get even harder. However, I think it's really crucial to do that, and I think we see in agriculture and also in a lot of other areas a increasing demand for climate services. However, I think one challenge is the scientific usability and predictability, and I think there it's probably hard to predict when such kind of events as right now in California happen. However, I think in terms of hydrological modeling, we can do a lot in terms of risk estimations and maybe work rather with risks in these areas. So those are the scientific challenges, but I think there are also a lot of usability challenges, and I'm not sure how your experience as a user with Climate Corp was, but actually, yeah, there is kind of another colleague of mine doing research on the different challenges that there are for users of climate services, and I think for sure there are also a lot of barriers to be that has to go out of the way. So I think we need more research for sure. We need more services. We need more people that actually talk to farmers and understand their need, and actually also translate those needs into the research, right? Because from the researcher's perspective, there's so many exciting questions to ask, but we don't always know if this is actually the most relevant information for the farmer. So maybe just my few thoughts on that.
Thank you.
Yeah, thank you. Jake, did you want to ask a question?
Hi there. Thanks for such a good room. I have a couple of questions. I'm curious as to whether or not this AI is going to have the oceanic conveyor belt data in it, and is there a sort of a future guesstimate of legislation. So, like the laws, maybe the long-term laws that are going to come into effect, whether or not that is also taken into consideration.
Sorry, just a follow-up question. What do you mean by future legislation?
So, like world laws, how they're going, if there is any kind of change that would affect it, similar to how America has pretty much pays the oil industry to make gas, but they're sort of ramping that down and making it more energy efficient, solar and wind.
Mm-hmm.
Whether or not that is added in to the artificial intelligence.
Yeah. So thank you so much. I think I will start with the last question. So we're basically looking at historic greenhouse gas emissions. So there is no, at least at the in our study, the overall model, it goes into the future and it has a CO2 emissions scenario, which is kind of the business as usual scenario. So there is a kind of no reduction of CO2, but there are a lot of different models which also actually do exactly model on how climate is going to be if we reduce our emissions to X, Y, Z. So basically, in that terms, we're just looking at the history and trying to predict there. So basically, no effects whatsoever. And in terms of oceanic interactions, so this is part of the model, but it's like we have the global climate model, the CANA SM2, which we're using there, and then there is the nested model. So I think we cannot. So it's implicitly it's there, but we don't have any explicit oceanic interactions in the AI in that sense.
I see. Thank you.
Yeah, thank you so much for those questions. And one last thing I wanted to ask, if you have a couple of minutes, is can your model, like the model that you created, could people use it to, let's say, a small country or even maybe a group of farmers or a district, to use the model to predict their local weather also? Let's say, the farmers, because I know that there are initiatives from IBM and so on to have like a open source create an
Hmm.
open source data set for different countries, also African countries, and could they maybe feed into their local data and then use your model to predict better, their weather and how to, plant crops, what type of crops to maybe plant in the,
Hmm.
for the next year and
Yeah.
so.
Yeah. So it would for sure be so the challenges, I think, also here going from kind of the overall climate situation to local weather. So I think what I could offer the farmers possibly is that they kind of look at their region in terms of kind of the second paper I was talking about in terms of clustering, and have a look at how are the local interactions with soil moisture for my region. And actually maybe learn from that. So it's unfortunately not a concrete model which tells you what will happen next year given the situation now, but at least it tells the statistics. And probably kind of before the local farmer, it takes probably a scientist and a data modeler who takes this knowledge into account and actually builds an operational model. So this is what I was mentioning. It's not really operational now because it's just low accuracies. So you need kind of more concentrated training to actually bring it to the farmer. But this is super important. And I think this is for sure the next general step that has to be taken.
Yeah, interesting. Do you think there will be non-code platforms in the future to help people with that so that they don't have to hire, their own data scientist? So for local poor communities, do you think, or is there already enough non-coding technology platforms that would, enable people to do that?
So I think there are several challenges in this domain. So I think one part is visualization, because we actually have a lot of real like different climate data, but it has to be kind of interpreted, and there are barriers in just opening the files. So I think in terms of visualization, we can still of our different models and prediction, we can still do a lot better as community. So I think that's kind of one work stream, and then probably the other one would be to promote climate services as well as on governmental, as also in the private sector, which are working with the data. And of course, like for the greater public good, and I think, there is a huge difference between climate services for, I don't know, big agricultural companies. Of course, they will be able to have some, but then for kind of the local farmer, that's probably too, or for the local farmer in a country in the global south that probably might not be accessible. So let's hope that kind of governmental institutions take over this role. I'm not sure if kind of no code solution would help there, because it's not just about the coding, it's more also about the physical knowledge behind the system, which you definitely need. That's why I think the no code solution is kind of just one step of many.
Yeah, why I'm asking this, because in a lot of developing countries, the people that are actually working the fields and contributing to most food source are women. And in a lot of countries, access to higher education for women is really not the reality. So empowering those women in kind of a form, where they have like intuitive platforms would be really helpful, I think. But that's another discussion.
Yeah.
And I'm really grateful that you came here and that you're working in this field and that you use because you could do this right now for Wall Street, right? You could use your brains to work on Wall Street and make millions and millions, but you're doing this. So congratulations. Thank you for doing this for humanity, and thanks for answering all of our questions and taking the time to be here. We really appreciate it. Thank you.
Yeah, thank you so much for the invitation. I really enjoyed it. And thank you so many for joining. I enjoyed the discussion a lot.
Wonderful. And I hope you'll come back one day. Maybe you'll come back, in a year or two and to give us some updates. That would be wonderful, or join our discussions. So you're always welcome back, of course. So, and thank you everyone for coming, asking great questions. This was a really interesting discussion because a lot of people participated. I always appreciate that. And if you like discussions like this, follow the club. And the next talk will be with Dr. Mekunoi, talking about novel fast charging lithium metal batteries. He will talk about that. And yeah, it will be, I
Katrina,
think,
can I say something?
yeah, go ahead.
Can I say
Yes,
something
go
quick?
ahead.
I think I just want to stress on the importance of independent and government research into this field, because a lot of insurance companies, they offer micro insurance and crop insurance in these field, and they have a lot of data and they can do a lot of accurate forecasting. But what they do is that wherever there is going to be payout, they don't underwrite the policies much. So they're actually, when there's a possibility of drought, they don't underwrite and don't insure that much, because they are their interest is more on their profitability. And on the, so yeah, I think this sort of independent research is more important. Yeah.
Yeah, thank you for that. Yeah, I agree on that. And then also, I think education, right? I think, is it Kenya? I don't know which country exactly right now. They have drought problems, and the president or the government wanted to introduce crops that are more heat and drought resistant, but there's like a high, resistance against using those GMO plants for various reasons and for many good reasons, to be kind of, to have kind of doubts about what the Western world brings to those countries. But I think in this case, there has to be like a very independent education about this, that don't have like interests of these companies in mind, that have really, independent, you know, researching of those crops and what is actually helpful for people and what not, without being paid by those industries. So, yeah, thank you so much for making that point. And Elisaveta, thank you so much. We wish you all the best and all the funding. And yeah, we hope to hear from you again one day. Thank you.
Sure. Thank you very much. Bye bye.
Bye. And I'll close the
Thank
room.
you.
Bye. Thank you. 3, 2, 1. Bye, everyone. Thank you.